Okay. So today we're going to pick back up thinking about mean arterial pressure. And we're going to be thinking about, right, how do we regulate this? How do we regulate blood pressure? Right? Thinking back to maybe that Parkinson's example that we started with, like that little video on the first day, right? Like his problem was that when he stood up, right, stumbled, felt faint, maybe fainted, partially because of his blood pressure, right? So as he stood up, he wasn't able to regulate his blood pressure, which he should need to do because we now know that the blood is affected by gravity, like everything else. Pulled down towards your feet, right? So when you stand up and you get a head rush, that's what's going on. But your body has mechanisms to notice that and fix that, hopefully pretty instantaneously. And it's when those mechanisms go wrong that you end up with actual symptoms of disease. Okay. So this is where we left off last time. We just reviewed how mean arterial pressure is related to other factors that we talked about in this class, right? So we started with that flow equation, right? And we know that when we're thinking about flow in the cardiovascular system as a whole, we can substitute in cardiac output, right? We know that flow is a difference in pressure divided by how much resistance we have in the system. So for a cardiac output, the pressure difference we're talking about is that mean arterial pressure. The resistance we would be counting is our total peripheral resistance, okay? Which means, because an equation is just a statement of a relationship rather than necessarily steps to calculate, right? And if we change the shape of this equation, we can now see that cardiac output and resistance are going to have an effect on our mean arterial pressure, okay, our average blood pressure, right? And we can even add in more because we know that cardiac output is our stroke volume. So the amount of blood ejected during that ventricular ejection phase of the cardiac cycle times our heart rate, so that we're getting this averaged over a minute, okay? So that we can match that average blood pressure, okay? So we need to account for our heart rate, stroke volume, and total peripheral resistance to figure out our mean arterial pressure. And as we regulate our mean arterial pressure, that means we've got three things to work with, right? So if we have a rise in blood pressure, right, what that means is maybe our stroke volume's gone up, maybe our heart rate's gone up, maybe our total peripheral resistance has gone up. And if we wanted to drop it back down, we're going to have to reverse some of those changes, right? So if we want to bring it down, right, we'd have to decrease our stroke volume, our heart rate, or our resistance, or all of them, okay? So we're going to be able to have these effects, bringing it up when it gets too low, bringing it down when it gets too high, by using nerves, so our neural control, and by using hormones, some of those signals that we have out in our bloodstream. Okay. But the first thing we have to do is notice that we've had a change to our blood pressure. So our first step, before we even get to regulating this, is that we need a sensor. And the sensor are baroreceptors. So like a barometer senses kind of pressure in the air. Baroreceptors are sensing essentially pressure or proxies for pressure in your cardiovascular system. So we're going to start with our low pressure baroreceptors, otherwise known as volume receptors. Okay. So, reminder, right, how these things are related, right? So when we have flow coming into a blood vessel, right, it pushes out on the walls, which hold pressure. Then as they pop back in, helps you maintain consistent flow to systemic organs. Okay. If we had a rise in blood pressure, right, this might be, for example, because we had a rise in cardiac output, right? So say your heart's racing, right? Say it's still squeezing the same amount of blood per minute or maybe even more. If we increase that flow, suddenly we have a lot more blood even than before here in the aorta. Mean arterial pressure is essentially average pressure for our aorta. So this is an increase in mean arterial pressure. Okay. But this situation, this assumption, comes with the assumption that our resistance is remaining the same, right? So if our flow increased, but our resistance went down, right, we might see a different situation. Okay. All right, so this is what an increase in mean arterial pressure looks like, and we gotta sense it. Okay. So determinants that are going in here, right, are all in that equation, but as we are changing or controlling our mean arterial pressure, we can think of different ways each of those factors are being controlled. So we've talked already about arterioles, right? So when we are thinking about our mean arterial pressure as our resistance, okay, times cardiac output, which is stroke volume and heart rate. Okay. We've already talked about controls on that arteriolar radius, right? So we know that a narrow little tube, right? Narrow little tube, lowered radius, higher resistance, right? So we've talked about how we can have vasoconstriction, right? Raising that TPR, right? Or we can have vasodilation, right? Lowering that total peripheral resistance, each of which would have an effect on our mean arterial pressure. Okay. We can also control stroke volume and heart rate as we talked about in A&P 1. We do want to regulate this stuff. We have to regulate this stuff because having the right blood pressure is important for your normal daily function, right? So it is a homeostatically regulated variable. Okay. So if your blood pressure drops too low, right? So if you have really low blood pressure, we refer to it as hypotension, hypo for low, less. Okay, so hypotension, not enough tension, right? Why this makes you feel faint or see stars is essentially you're not getting enough blood flow to tissue. Okay, so when you see stars or feel faint, this means not enough blood, not enough oxygenated blood, all that good stuff. It's getting to your brain and your eyes, right? And it's just that instant, right? But we are seeing a drop in blood flow, right? Which means that tissue is experiencing low oxygen levels, not getting rid of its carbon dioxide as fast as it might like to. So this has pretty immediate noticeable effects when you're not getting enough blood flow to tissue. Hypertension, so too much pressure, hyper too much, is also a problem, but more of a long-term problem, right? So you probably notice if your blood pressure drops super low, right? You'll feel dizzy, right? Hypertension, still a big problem. If you go to the doctor and you notice that they're going to give you pills, tell you to change your diet, things like that, right? But this is more because of its long-term effects on organ systems, right? So you're getting enough blood flow towards tissue minute by minute, But this is also putting stress on all these structures that carry that blood, right? If you always have high pressure on the walls, right? You're kind of straining those blood vessels a little bit, right? They're constantly a little extra dilated because of all this flow going through all this pressure, right? That's a stressor. And your heart, right, if it also has lots of pressure to fight against in the arteries, right, then that's going to make your heart have to work harder, and long-term stresses your heart and your blood vessels out. Okay, so that's why hypertension to high blood pressure is also a problem. So in that short-term regulation, seconds to minutes, we're going to start by regulating our cardiac output and our total peripheral resistance using the heart and our blood vessels. Okay, so this is what your body has to do when you stand up, right? So that you don't feel faint, don't feel dizzy, right? We're going to have to immediately regulate a tiny little drop in blood pressure. This mostly involves neural control, right? So this is your nerves involved here, because nerves can work pretty fast, right? They just have to send their action potentials. Okay. So that's a quick response as soon as we have our baroreceptors noticing our change in pressure. Long-term regulation is a bit trickier, right? So if you have a long-term change to blood pressure, and it's often common, definitely what we talk about when we talk about hypertension, right? If we want to fix long-term changes to blood pressure, we're not going to want your nerves to be like constantly reporting on that, constantly fixing it, right? Because our sympathetic and parasympathetic nerves are also helping us respond to day-to-day life. Right, so if they're constantly changing their firing due to a long-term problem, that's not going to work too well. So what we do for long-term regulation on the order of like minutes to days is we have enough time to trigger like hormones and stuff, right? And we're going to end up regulating the blood volume rather than the constriction of the heart and the arterioles. So we're going to try to leave the cardiovascular system alone. What we're going to try to do is, if we have too much pressure, we're going to try to adjust, make it less pressure by just having less blood in those blood vessels, or the opposite. Okay. So this is going to require our kidneys to get involved. So we'll think more about exactly how this works when we get to the renal system. Questions at this point? Okay. So before we move on and go through like a little flow of how this can work, let's make sure, remember this thing that I've been saying a couple times now. So what are our factors that we're tracing as we're determining our mean arterial pressure? We want the answer that has nothing extra and nothing left out. I'll give you another couple seconds. Okay, cool. All right. So yeah, when we are talking about that mean arterial pressure, right, that's math. The three factors that we need to know about flow, which is cardiac output, which is stroke volume times resistance times heart rate, excuse me. And we need to know about resistance, which is our TPR. So those are the three factors listed out here in our top answer. Right, so when it gets to the exam, if we say anything about a change to any of these three things, we're going to expect there to be a change in that blood pressure corresponding. Okay. So for the second answer, right, it's not the atria specifically where we need a pressure, right? So our MAP, our mean arterial pressure, is measured for the aorta, essentially. Right, and we definitely need some resistance added into this, which isn't in this list. For this one, we're almost there, right? But what we don't notice is that heart rate and stroke volume are the same thing as cardiac output, right? Those are equivalent statements, right? Heart rate and stroke volume together make up cardiac output. So we're still missing our resistance. Okay. And again, this last one, atrial pressure isn't really important for our blood pressure overall, except as it is related to our end diastolic volumes and stuff we talked about with the veins. Okay. Right. So I'm going to start with that short-term regulation, right? The neural control. So we're going to see that we have neural control, especially in the form of negative feedback loops, right? So specifically, what we're going to be detecting is when we have changes to the blood pressure, drops to the blood pressure, right? A negative feedback loop means we're trying to reverse that change, right? So if we have a drop in blood pressure, we need to bring it back up, right? So that's our negative feedback, right? Change one way, bringing it back to its original value, right? At which point we can shut off all the mechanisms we've used to put it back to normal. Right, so our detectors for this neural control of our MAP is going to be those low pressure baroreceptors. Okay. When we talked about homeostasis, we talked about the fact that we also want to have some type of integrating center, right? Something that pulls in information and then determines the response, right? Which may involve multiple systems, might involve other systems than the one giving us the signal. And so in your brainstem, you have cardiovascular centers that help regulate blood pressure. Our controllers, so like the nerves that are going out and helping us actually change the blood pressure. It's that autonomic nervous system, right? So sympathetic, parasympathetic. Right, autonomic nervous system is going out. And our effector organs are going to be the heart, so like cardiac muscle, as well as now our blood vessels. So we're thinking things like our arterioles. Okay. So the low pressure receptors have corresponding higher pressure receptors, okay, sometimes called stretch receptors. So those volume receptors, those low pressure baroreceptors are really telling us stuff about veins. Our pressure receptors elsewhere are telling us kind of about stretch. Okay, so the places we would see those are the aortic arch, right, coming out of our heart, right? So we've got a pressure receptor pretty immediately as soon as we have blood exit the heart. Right, so we'd have an immediate signal about what is the pressure coming out of our heart. Our brain is super important. So we also have arterial baroreceptors, these pressure receptors in the neck in a region called the carotid sinus, because it's your carotid artery that's carrying blood up to the brain, right? So we have a common carotid artery, then we have a branch into internal and external carotid. Internal carotid is shooting up to your brain, powering that circle of Willis from the front. Okay. So we're checking that we have enough pressure, the right amount of pressure coming into the heart. We're checking that we have enough pressure, the right amount of pressure going up to the brain, essentially. Sometimes these are referred to as stretch receptors because the way you would sense changes to pressure would be to sense stretch or lack of stretch in those blood vessel walls, right? That's what the pressure receptor can respond to. So then that control center, the integrating control centers are in the medulla oblongata. They coordinate the response that we're going to see in a second, basically. So how we do that? I've been talking about what happens when you stand up. So we're about to talk about the baroreceptor reflex. What do you think is going to happen? So we have arterial pressure falling, okay? And the baroreceptor reflex gets activated in this situation. So what are we going to want to do? Okay, take another second or so. All right. Okay, so let's talk about this. All right, I'll redraw a little lower. Okay. So the situation we're setting up, right, is we're starting this baroreceptor reflex is talking about when we start out with a drop in mean arterial pressure because gravity is pulling our blood towards our feet and we're sensing our blood pressure. Right now we know we're sensing it as it comes out of the aorta, we're sensing it up in the neck, right? So it's up in the neck, but your blood's getting pulled towards your feet, right? You're going to sense a drop in blood pressure, okay? So what we're trying to do is correct that change, okay? So we're going to be looking for things that can do negative feedback, pulling that mean arterial pressure back up, right? That's the reflex that's supposed to happen when you stand up, right? You're supposed to have a reflex that immediately gets your blood pressure back up so that you can keep thinking, keep being conscious, keep getting blood to your brain. Okay. So we're looking for factors that can increase that mean arterial pressure as part of this reflex. Okay. So let's step through the wrong answers first. So this most common one that we picked was the vasodilation of the arterioles. Okay. Someone want to remind me what vasodilation means? When they get wider, right? So vasodilation of an arteriole would mean we have our arteriole dilating, getting wider, which we might express as a rise in the radius, right? But what we care about in this equation for our mean arterial pressure is not the radius, but the resistance, right? So this is going to be equivalent to a drop in resistance, okay? So the change we create with vasodilation of the arterioles would be in the same direction as that problem we're trying to fix, right? We have a drop in resistance in an arteriole. We have a drop in total peripheral resistance, right? That's not going to help us fix our suddenly low fall in blood pressure, right? It would make this problem worse. Okay, so we don't want to dilate them. Let's think about stroke volume next. Okay. Got the same sort of problem here, right? So if we decrease either our stroke volume or our heart rate, okay, if we do either of those things, we're also going to be decreasing that mean arterial pressure. So again, we're going to be reinforcing this problem, right? Which we don't want to do. We want to get that reverse direction. We want to get it back. Parasympathetic activity, right? This takes thinking back to chapter 13, right? But we know that parasympathetic activity, what it affects, right, is the heart. Right? It's not really affecting our blood vessels, at least not that we've talked about so far, right? But what it can do is drop that heart rate down. Okay? Drops the heart rate down, still making that problem of our blood pressure drop worse, right? So the correct answer is decreasing the compliance of the veins, right? And this takes thinking back to what we talked about as we stepped through understanding the veins last week, right? So this is that whole big flow chart, but essentially, right, we know that compliance refers to a relationship between pressure and volume, right? So for high compliance, we can hold a lot of volume with not very much pressure. Low compliance, the opposite, even a little bit of volume is going to make a big difference in pressure. Okay. So if we decrease venous compliance, right, what we're saying is we've lowered it. So we've made that vein more like the situation we usually have in our arteries. Okay. Which means essentially that we're dialing up that pressure, right? So if you suddenly lower compliance, but you had some amount of volume, right? Now that same amount of volume is going to create a higher pressure with this change in compliance in the walls of the veins. So then we have to think about the heart and how it fills. Okay. So we have our heart. Okay. Veins are coming into our right atrium. Okay. From multiple places, actually, right? Okay. But what has to happen for that heart to fill, right, is we need a pressure gradient, right? So we need low pressure in the atrium, higher pressure in the vein. Okay. So if we decreased compliance, we've increased pressure, right? We've increased pressure. So essentially what we've done is made a bigger pressure gradient, right? And we can even think about that flow equation right here with this local part. We wouldn't be thinking about cardiac output anymore, right? But what we're saying is now we're thinking flow into the heart. We've increased that change in pressure without doing anything to the resistance, right? So if we increase that pressure difference between the vein and the atrium, right, we're going to increase flow into the atrium. And this has downstream effects, right? This means that as the heart fills, more blood gets into the heart. We have more blood in the heart. When we squeeze, we eject more blood out of the heart. So essentially what we're doing by decreasing compliance of veins is we're raising stroke volume. Okay, so this is the only one in this example that goes the appropriate direction. Right, so as we increase stroke volume, leaving all else equal, we'd increase that mean arterial pressure as well. So of this list, that's the only thing that can fix our problem. Okay. So a lot of ugly scribbles I've done on the board, but questions about this question at this point before we talk some more about that reflex. So these are the kind of steps you're going to want to think through as we think through questions about what's affecting our blood pressure or mean arterial pressure. You're going to want to think piece by piece, one by one. Oh, looks like I pulled the diagrams that were relevant here from last time, right? So we think about flow and pressure, we think about compliance. And in that specific example, we needed to pull in our knowledge of what's going on with our veins. Okay, so we've got these negative feedback loops. Our detectors, our baroreceptors, our controllers are going to be things like our autonomic nervous system, right? And actually we can see the portion of our autonomic nervous system that affected the veins there, right? Sympathetic nerves to veins, decreases venous compliance, ultimately increasing our cardiac output due to an increase in stroke volume, which raises our pressure. Right, so the nervous part, the extrinsic control part, is that sympathetic nervous system piece. All right, so like when we were talking about the heart, sympathetic nervous system is going to be able to do like more things when we're thinking about our blood flow, blood pressure. Okay? We are going to have a little bit of parasympathetic input, right? Because we know that we can change heart rate, really, mainly with our parasympathetics, right? So we know, let's see. Let's map these on, right? Okay, so we have stroke volume, heart rate, total peripheral resistance. All right. So for our parasympathetic input, we know the only place that the parasympathetics really go in the cardiovascular system that we talked about is the heart, and not even the whole heart, right? Parasympathetics, when we look at that map, they've got to come from our cranial nerves or down from our pelvis. The ones for our heart come from the vagus nerve. All they go to are our pacemaker cells. Fortunately, they go to the sinoatrial node as well as the AV node, right? This is our pacemaker overall for the heart. And the effect of parasympathetic input to the heart is that it decreases heart rate, right? So parasympathetic input, therefore, when we have that parasympathetic rest and digest portion of the nervous system active, we're going to drop down our blood pressure. Right? You don't need to pump your blood so hard, so forcefully to tissue. You're just sitting around doing nothing. Right? It's when you're fighting, flighting, that sympathetic response that you're going to want to peel that blood pressure up so that you're also getting more blood flow to your tissue. So we see a lot more effects with the sympathetic nervous system. Pretty much all of them, though, are going to end up raising our blood pressure, right? So sympathetic input overall, fight or flight, raises our blood pressure, which also affects flow. This is all sort of give and take back and forth between all these factors, right? These are relationships, right? So we want blood flow to our organs. We can do that by increasing pressure coming from the heart, because that's going to increase flow to each organ. Okay? So starting with the heart, from last semester, we know that the sympathetic input also goes to those pacemaker cells, but what it does is the opposite to what the parasympathetics did. So instead of lowering heart rate, rest and digest, that was our parasympathetics. Sympathetics raise the heart rate. Okay. And we know that the sympathetics actually also go to the ventricles. So we didn't have any parasympathetic innervation of the ventricles of the heart, just to those conducting cells, those pacemaker cells in our electrical system. But the sympathetic nervous system has more branches to the heart. And because it goes to the ventricles, it can also make those ventricles squeeze harder. So it increases contractility of the ventricles, makes them squeeze harder, same thing. Which means we are increasing the stroke volume, the amount of blood squeezed out every heartbeat. Okay. Now, here's where we add on what we've talked about this semester, right? So what we've been talking about. Arterioles, I have that resistance, right? This is what creates our total peripheral resistance for the most part, right? We're adding up resistance in every arteriole. We know that arterioles, if they're responding to nerves, the reason for that is they have those adrenergic receptors, especially those alpha adrenergic receptors causing vasoconstriction when we have things like norepinephrine coming from the sympathetic nervous system binding to them. So that overall effect of sympathetic innervation, activating those alpha adrenergic receptors throughout the body, is to raise our total peripheral resistance. Okay. Finally, for the veins, we had a more complicated flow, but that's what we just did on the previous slide in that question, right? So when we had an increase in venomotor tone, again, due to that norepinephrine and alpha receptors in the veins, right? Venomotor tone is talking in a different words about that contraction state of the blood vessel walls of those veins, right? So venomotor tone, more venomotor tone, these are a little more tight, a little more constricted, right? When they're tighter, when they're tenser, when they have more tone, this is that drop in compliance, right? So that drop in compliance means that now that same amount of blood is causing higher pressure, causing the heart to fill more, causing greater cardiac output. So this change in venomotor tone due to the sympathetics, actually of these factors, is really affecting that stroke volume, right? So greater end-diastolic volume and diastolic pressure means we have greater amount of blood squeezed out when the heart ultimately does contract. So all of these effects of the sympathetic nervous system come together to raise our mean arterial pressure. So when we think about our baroreceptor reflex, again, looping back to that previous question, right? It's about a response, an automatic response to a drop in blood pressure. We're going to expect these sympathetic effects to be highly involved, right? So we're regulating that with our nervous system, extrinsic control of the blood pressure, right? It's all of these sympathetic responses are ways we can pull that blood pressure back up. So here we can see those connections, in case you don't recall, between our nervous system and the heart, right? So here we have our parasympathetic cranial nerve, the vagus nerve, just going to that SA node. Our sympathetic nerves have to synapse in the ganglia of the sympathetic chain, at least most of them. Okay. After they do that, they have projections to both the SA node and that ventricular myocardium. They also have sympathetic nerves that are going out to the arterioles, also have sympathetic nerves that are going out to the veins. So the sympathetic nervous system is kind of all over the place in the body. Doesn't have to travel that far necessarily though, because we recall those sympathetic nerves, they come from that thoracolumbar region of the spine, right? So they're kind of right there in the rib cage already. Okay. So how do you think the baroreceptors in the arteries, so in the aorta and in the carotid sinuses, are going to help change that mean arterial pressure? What do you think they're going to do? Take a couple more seconds. Take a look. Okay, cool. All right. So what's different here in this question versus what we talked about in the previous question and on the previous slide is we're looking for kind of like a mechanism now, right? We're not asking what is changing in the body. We're trying to think about how the arterial baroreceptors actually do that. So this comes to that homeostasis bit, right? So way back when we talked about how when we have something we're regulating through homeostasis, right? First, we need to notice the change, right? Our error signal, right? And then we have to have nerves coming back to our central nervous system, right? So we have a sensor that senses the change. And then we have those afferent nerves, those sensory nerves that we don't often talk about, but they are important to your body. Okay. They go back into your central nervous system, which is where we have our integrating center, right? And then that central nervous system sends our response through our efferent nerves, okay, to our effector organs to make an effect. So all of the other answers, right, they are correct in that we do need total peripheral resistance to change. We do want our heart rate to change. We do want our stroke volume to change. But the first step of this process is going to be telling your brainstem that we actually have a problem. So the first thing that they need to do is to send a signal to the central nervous system. Cool. All right, so we're going to walk through this baroreceptor reflex one by one. So what we start with is by noticing this drop in pressure, right? So we're thinking about standing up, pressure drops, right? So we know that there's a drop in blood pressure. Then we have our sensor, right? So the sensor is those arterial baroreceptors in the arch of the aorta and in those carotid sinuses. And the way this actually works is the baroreceptor, it's got to send a signal with action potentials, right? So what's usually happening is think about like a blinking light, right? So the baroreceptor is always sending a signal, just like kind of a pulse to your brain. And the way that we send a signal that we had a drop is just that frequency of the action potential starts going down, right? So they're getting slower, right? The baroreceptor is now projecting action potentials more slowly to your central nervous system. So we have a drop in those frequencies of the action potentials in those sensory nerves coming from the arterial baroreceptors. Okay. So this is what your cardiovascular control centers in the medulla oblongata are going to notice, right? Okay. So they're going to be managing our response. So the first thing that we're going to want to do is turn off anything that's going to compound this effect, right? So parasympathetic activity keeps your heart rate low, right? Actually, it keeps your heart rate lower than the baseline rate of those pacemaker cells in the SA node. They want to be at like 100-ish beats per minute, but because the parasympathetic nervous system is active, your heart rate should be lower than that. Okay, but if your blood pressure is dropping, your cardiovascular control center says, okay, nix all of this parasympathetic activity. We don't want a low heart rate anymore. So we're trying to get that blood pressure back up. So we're dropping our parasympathetic activity, which means that action potential frequencies in that SA node, those pacemaker cells, start speeding up. They set the pace for your heart. So your heart rate goes up. Okay. When heart rate goes up, that means your mean arterial pressure is also going to go up, because that mean arterial pressure is just stroke volume times heart rate times our resistance. the other part of this, right? At the same time, your cardiovascular control center is saying, okay, so it's probably not going to be enough to just pull our heart rate up. We're going to do everything kind of all at once. So we're also going to increase sympathetic activity to the body. So by increasing that sympathetic activity, we're not just turning off those rest and digest signals that have been suppressing the heart rate. We're also going to make some changes in that direction that's going to bring our mean arterial pressure back up. Okay. We have lots of versions of those changes, right? So one is that we're also going to affect that SA node and bring the heart rate up, right? Sympathetic activity can put it above 100. We're also affecting stroke volume by affecting that ventricular contractility, right? We increase how hard the heart contracts, means we increase our stroke volume. In the veins, we increase venomotor tone, which decreases in compliance, which means we've increased that pressure in the veins going to the heart. Which is actually great because we now have a bigger pressure difference between those veins and the heart, means the heart can fill more. So we have greater end diastolic volume, which also means we increase our stroke volume because we have more blood in the heart. We can squeeze more blood out of the heart. Okay. Finally, the arterioles. Sympathetic activity means those nerves are releasing their norepinephrine. Arterioles have those alpha receptors out throughout the body. Response to the alpha receptors getting triggered is vasoconstriction. Okay. When we vasoconstrict, we decrease the radius, increase resistance. Overall effect is to bring up total peripheral resistance. So all together, we have increased the blood pressure. This is a negative feedback loop. We go back to our normal kind of baseline situation after this, once we've fixed our problem. So this whole big map of stuff, right? This is our baroreceptor reflex. So this should be happening without you noticing every time your blood pressure drops. Baroreceptor reflex. Okay. So we will pick up here next time. I'll send you some advice, but make sure to review some of this material in your book until it sinks in.